Welcome back, everyone. This is Professor Herring. In this video, we're going to learn more about gases. Specifically, we're going to learn about how gases compare to liquids and solids and discuss how the kinetic molecular theory explains this behavior. We're then going to look at other applications of gases and specifically looking at their kinetic energies and the speeds of gas particles and how that relates to what we call a Boltzmann distribution that looks at a distribution of gas particles. And then finally, we're going to finish up by calculating the root mean square speed of a gas at a specific temperature. Let's begin. So gases are different from solids and liquid. Gases will occupy the size and shape of their container. If you take and empty a room of everything, you use a what's called a vacuum to suck out all of the air and all the particles within it, and then you insert into that any given gas, it's going to fill up that container. It's going to fill the space of the room. If you then take all those particles and put them into a smaller container, it's going to fill that container. And so we see that the volume can be easily modified. They also exert a pressure, and we're going to talk more about what that is, but essentially that relates to the collisions of the gas particles on their container. They tend to have low densities and are compressible. So we can take a large volume of gas and compress it down into a smaller volume. And you can see that there is, while this is a zoomed in version on gas particles, that there's space in between those gas particles. They are going to fill up their container, whereas liquids only will fill the bottom part of the container, and solids will take a very definite shape. And so we want to discuss what's going on the molecular level that gives rise to these different properties. To answer this, we need to take a look at the kinetic molecular theory of gases. This describes how gas particles are in constant motion. And not only that, but there's other specific assumptions that we make about ideal gases. First is that while they're moving in straight lines. They don't curve around, and their direction is random. They're moving in all different directions. The molecules themselves, the gas particles themselves, are essentially infinitely small. They occupy no size themselves, even though the gas as a collection fills the container. And so we might describe this as saying the volume of the container is much, much larger than the volume of the gas particles. The molecules do not attract or repel each other. There's no intermolecular forces. Because of that, when they collide with each other, there's no energy that's lost. So whether they collide with another gas particle or the container, there's no energy lost, although it can be transferred. And then finally, we have this idea, and that's the average kinetic energy is proportional to the temperature of the system in Kelvin. And that's specifically talking about the average or the mean kinetic energy of our collection of gas particles. So what does this all look like? We're going to open up an application that you can find within the ebook to take a look at that. So in here, what you can do is you can see the gas particles moving around. And if it's a little choppy in this video, then I recommend going and taking a look at this application on your own. But what we're going to do is if we have right now just helium particles bouncing around. What you'll notice here in the middle of the screen, we have a distribution of speeds. In other words, not every particle is moving at the same speed. And if we were to trace a given particle, what we can do is we can see that it is really moving in random motions in a straight line, and that its speed changes. In some cases, it goes very fast. In other cases, it goes very slow. If we increase the number of particles, we can see down below that our pressure is changing, but that our average speed does not change. In fact, one way to show this, let's go back to our original setting. If we have this sum all of the speeds over time, we can see that we get that curve. And we can see that Again, as we change the pressure or the number of particles, initially we might get some disruption of our system, but overall it's going to go back and form the average, that distribution, what we call the Boltzmann distribution. If I change the temperature, we can see that that changes our distribution. Higher temperatures are going to lead to higher overall speeds, whereas lower temperatures lead to lower overall and average speeds. Changing the volume also has an effect. If I decrease the size of my container, I'm going to increase the pressure. And while the speeds might momentarily shift, the average speed, or the speed of the average for the system, does not change. Finally, let's go back to our original settings. And if we insert a second gas, let's go to equal volumes, or equal number of moles of each. We can see a phenomenon, a couple interesting things. Looking at the distribution of helium, we see that it has a peak at around 1,000 meters per second. For neon, it's much different. And if we plot both of them at the same time, we can see that for heavier particles, meaning the neon, on average, they're moving slower than the lighter helium particles. Despite these averages, we do get a distribution. In other words, some of the helium particles are moving slower than some of the neon particles. And this just arises from the statistical nature of what's going on. We've got a collection of particles, and their speeds are distributed over all of the possibilities that we can see. Something to note here as well is that there is a lower limit, 0 meters per second. However, the upper limit actually is essentially infinite. We tail off at the end and don't actually reach to 0 at these high speeds. Let's return back to our slides. So what do we notice about the speeds? Well, there's a distribution, right? They're not all moving at the same speed, and it varies. If we increase the temperature, we saw that increased temperature lead to increased speed. When we added in the neon, we saw that neon was slower than helium. And when we changed the container, we saw that speed stayed the same, but pressure goes up. So hopefully that helps you to understand a little bit more about the behavior of gas particles. Let's talk about pressure. Pressure is essentially a force exerted over an area. And when scientists have done studies about pressure and volume, number of particles, the speeds, they have found that the pressure is indirectly proportional to the volume. So if your pressure goes up, your volume goes down, or vice versa. But pressure is directly proportional to the number of particles and the mass of the particles, as well as the average speed. And so if you have a set number of particles and you increase the speed at which they are going, then there's going to be an increased pressure. And that's because those particles are hitting with a larger force. If you increase the mass of those particles, then they also have a larger force, and they're going to the pressure is going to increase. However, if you increase the volume, you're going to be increasing the area. And so the particles are going to be hitting less frequently, and therefore decreasing the total pressure on the container. We can also talk about temperature related to the speed of molecules. We said earlier that temperature is related to energy, to average kinetic energy. We also know that average kinetic energy is related to 1/2 m, which is the mass of the molecule, and the root mean square speed of the molecule. That combined that gets us this distribution. What we see is molecules are moving at different speeds. And so if you have a large collection of molecules, that their energies and their speeds are going to follow a pattern called the Maxwell-Boltzmann distribution. What we see here is that we have a most probable speed. And that means that's going to be has the highest proportion of molecules at this speed. But notice, because it's not symmetrical, because there's a it's slightly weighted towards the higher end, that our average, what we're going to call the root mean square speed, is slightly higher than the most probable speed. And so when we take a look at the various variables that are affecting the RMS speeds, we can see that when you do these experiments, we see that the temperature is going to increase the average kinetic energy. If we change the speed or change the temperature, our speed increases, and therefore the average kinetic energy increases. And we also see that the molar mass has an effect as well. By changing the molar mass but keeping the same temperature, we see that the speeds are changing. And so at a fixed temperature, on average, the heavier molecules are moving slower than the lighter molecules while they're at the same temperature. Again, at the same temperature, if you have two different types of molecules, in this case, or more, if you have multiple types of molecules, the heavier molecules, the ones with higher molar mass, are going to move at a slower speed. And that's because they have, on average, the same kinetic energy. And since we saw that the kinetic energy is proportional to both the mass and the speed, if your mass goes up, as measured by these are related or indirectly related to each other. So if your mass goes up, your speed must go down. So when we combine all of this together by looking at the average kinetic energy and the temperature, along with other relationships involving the number of particles and the observations that we make in the lab, we can rearrange this and actually calculate the average, or the speed of the average particle. And this is, we use this equation. I'll demonstrate how to do this here on the next slide. So let's talk about the root mean square speed. The root mean square speed is the speed of a particle with the average kinetic energy of the entire sample. So you take your whole sample of particles. We have this box, let's just say. And there's these particles moving around in it. Some are moving fast, some are moving slowly. If you take the average kinetic energy and you relate that to the speed, that's the RMS speed. The root mean square speed is the speed which a particle has if it has the average kinetic energy. So let's do a calculation here. What's the RMS speed of nitrogen gas at room temperature, 25 degrees Celsius? So we have our equation here. We have our temperature, but we need to convert to Kelvin. The way that we do that is by taking the temperature in degrees Celsius and adding 273.15 degrees. That will get us our temperature in Kelvin. The molar mass is found by taking the atomic mass of nitrogen times 2, because there are 2 nitrogen atoms. So that's 28 grams per mole. However, we need to convert this to kilograms per mole. And the reason for this is because of our gas constant, R. And that's because a joule is equivalent to a kilogram meter squared per second squared. So when you take a look at the units of R, we really have kilograms meter squared per second squared per mole per Kelvin. And so because it's in the numerator, our kilograms per mole is going to cancel with our molar mass. Our Kelvin is going to cancel with our temperature. And then because we're taking the square root, we're going to end up taking the square root of meter squared per second squared, and that's going to get us a speed in terms of meters per second. This value of 3 comes from the fact that we're looking at, we're taking and simplifying what is a three-dimensional velocity into a single-dimensional speed. So if we solve for this, we get a root mean square speed of 515 meters per second. That's actually really, 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 really fast. Now let's take a look at what's the effect on changing the temperature. If we keep a constant molar mass, if we're looking at nitrogen again, molar mass of 28 grams per mole, but we change the temperature of the system, what we see is that the root mean square speed increases. At about 100 degrees Kelvin, we see that we're somewhere around 300 meters per second. 300 degrees Kelvin, that's what we just calculated, just above 500 meters per second. And at 1000 Kelvin, we're somewhere around 900 meters per second. What we also notice is that the overall shape of the Boltzmann distribution is modified slightly. So we end up with a flatter curve at higher speeds. We're getting more molecules that are moving more quickly. Again, the y-axis of all of these graphs is looking at the proportion or the percentage of molecules that are at a given speed. So for this particular one, we see that we have roughly 0.33% of all molecules at 100 Kelvin have a root mean square speed of approximately 300 meters per second. If we sum up every individual vertical slice for a given curve, that should add up to be 100%. So that's it for this video. If you do have questions, please ask on Piazza in office hours or recitation. Thanks for watching and have a good day. Bye.